Here I have three pictures of the same carbocation, and a carbocation has a carbon that's positively charged, which we call a cation in chemistry. So if you take these words, carbon and cation, and combine them, you get carbocation. Let's look at the picture in the middle first. So this carbon is positively charged. Normally, carbon has 4 bonds to it, but here it has only 3. So here's 1, here's 2, and here's 3. And because it has only 3 bonds, it has a +1 formal charge. And carbocations are very reactive because carbon likes to form 4 bonds. Let's look at the same carbocation over here on the left, and the carbon in magenta, the one with the +1 formal charge, is this one. And since we aren't drawing in our atoms on this bond line structure, sometimes students forget that because this carbon in magenta has a +1 formal charge, that means it must have a hydrogen bonded to it. So don't forget about that when you're looking at bond line structures. Finally, let's look at this same carbocation on the right. The carbon in magenta is right here. That's the one with the +1 formal charge on it. Because the carbon in magenta has only 3 bonds to it, this carbon is sp2 hybridized. And we know from earlier videos, an sp2 hybridized carbon is going to have an unhybridized p orbital. So here is our unhybridized p orbital. And also the geometry around that sp2 hybridized carbon is planar. So let me see if I can sketch in a plane here indicating the atoms that are directly bonded to that carbon are in a plane around that carbon here. Now let's look at a model of the same carbocation. Here is our sp2 hybridized carbon, and here is our unfilled p orbital. On the left, a methyl group is directly bonded to that positively charged carbon, and on the right we have another methyl group. So 2 alkyl groups are bonded to that positively charged carbon, and we call this a secondary carbocation since it has 2 alkyl groups directly attached to the positive charge. And these alkyl groups can help to stabilize our carbocation. So let me go ahead and show that. So some of this electron density in here in this bond can be donated to this empty p orbital, and opposites attract. So donating some electron density helps to stabilize the carbocation. So alkyl groups stabilize carbocations. This alkyl group on the right can do the same thing. So some electron density from in here can help to stabilize our carbocation. But notice in the back, our hydrogen, right, the electron density in this bond can't be donated into the p orbital. So the geometry isn't right. So alkyl groups stabilize carbocations and hydrogens do not. So it makes sense that the more alkyl groups you have, the more stable your carbocation. We just saw that alkyl groups stabilize a carbocation by donating electron density to the empty p orbital. This effect is called hyperconjugation. So as you increase in the number of alkyl groups, you should increase in the stabilization of your carbocation. So let's look at this carbocation on the left. There's only one alkyl group directly bonded to this positively charged carbon. So we would call this a primary carbocation. In the middle, we have 2 alkyl groups directly bonded to this positively charged carbon. That would be a secondary carbocation, like the example in the picture above. And finally, if we have 3 alkyl groups directly bonded to our positively charged carbon, that would be a tertiary carbocation. The more alkyl groups you have, the more you stabilize your carbocation. So a tertiary carbocation is more stable than a secondary carbocation. And a secondary carbocation is much more stable than a primary carbocation. So these are so unstable they might not even exist. So we'll focus on secondary and tertiary carbocations. Now that we understand carbocation stability, let's look at an introduction to carbocation rearrangements. One possible rearrangement is something called a hydride shift. So first, let's study what a hydride ion is. We know that hydrogen has 1 valence electron, and if you take away the 1 valence electron from hydrogen, you would be left with H+, which we know is a proton. But if you added an electron to a neutral hydrogen atom, you would now have 2 valence electrons. So let me draw that in there, which would give this a -1 formal charge, and that is a hydride ion. So hydrogen with 2 electrons and a -1 formal charge is what's called a hydride. So a hydride shift could occur to form a more stable carbocation. So let's look at this carbocation here. We know that this carbon has the +1 formal charge. Here's one alkyl group, and here's a second alkyl group. So this is a secondary carbocation. And we can do a hydride shift. Before I show how to draw a hydride shift, let's go to the video so we can see it with the model set. So here is that secondary carbocation. You can see the geometry around our sp2 hybridized carbon is planar. You can also see our empty p orbital here with the paddles. And we have two alkyl groups directly bonded to this carbon. On the right, there's a methyl group, and on the left, we have this big alkyl group. And in the back, we have a hydrogen. So notice that we are donating some electron density from this bond into our empty p orbital. We know that helps to stabilize our carbocation. But let me just take these paddles off here and let's show a hydride shift. So remember, a hydride is a hydrogen and its 2 electrons. So I'm going to take this hydrogen and these 2 electrons in this bond, and I'm going to show a shift from this carbon to the carbon on the right. And that's a hydride shift. Now, on the left, we took a bond away from this carbon, so that should be positively charged, and it should be planar or flat, but it's not because of the model set. I had to use a tetrahedral carbon here, so I'll show a new model set in a minute to show that it actually is planar. And on the right, this should be tetrahedral. This carbon went from being sp2 hybridized to sp3. So let me get out the new model set here so we can better visualize what the carbocation actually looks like. So this carbon is our sp2 hybridized carbon now, and you can see it's planar around that carbon. And this is a tertiary carbocation. We have a methyl group here, a methyl group here, and then an alkyl group over here. So a tertiary carbocation is more stable than a secondary. You can also see at this carbon, now we have an sp3 hybridized carbon here. So the geometry around that carbon is tetrahedral. It went from being planar to tetrahedral geometry. Let's draw the hydride shift that we saw in the video. So attached to this carbon, we know there is a hydrogen, and this hydrogen and these 2 electrons can move over to this carbon on the right to form a more stable carbocation. So let's draw in that new carbocation. So let me draw this in here. I'm going to draw in that hydrogen in red, and let me go ahead and highlight it in red here like that. And notice we're taking a bond away from this carbon on the left. So that's this carbon here. And that's a tertiary carbocation, as we saw in the video. So we need to put a +1 formal charge on this carbon. Notice that there was a hydrogen on this carbon to start with, and it's still there in our tertiary carbocation. You can see it better in the video. But the goal is to form a more stable carbocation in a rearrangement, and we go from a secondary carbocation on the left to a tertiary carbocation on the right, which we know is more stable. Finally, let's do one more kind of carbocation rearrangement. This one's called a methyl shift. So this carbocation is secondary. The carbon with the +1 formal charge is directly bonded to a methyl group and this alkyl group over here. So for a methyl shift, we could take this methyl group here and we could show this methyl group moving from this carbon on the left to this carbon on the right. Let me go ahead and color code. So I'm going to say the carbon on the left I'm referring to is red, and the carbon on the right that I'm referring to is blue. So the methyl group shifts from the carbon in red to the carbon in blue, and let's show the result of that methyl shift. So now we would have a carbocation that looks like this. So the carbon in red loses a bond. So here's the carbon in red. It's sp3 hybridized, it's tetrahedral. But when it loses a bond, here's the carbon in red, now it's sp2 hybridized and has planar geometry with a +1 formal charge. The carbon in blue, let me circle that here, it was sp2 hybridized and planar, but it's gaining a methyl group, right? So here's the methyl group that it's gaining, and this is the carbon in blue, and it goes from being sp2 hybridized to now being sp3 hybridized. So remember, there was a hydrogen on this carbon in blue to begin with, and it's still there for our carbocation. So this is a tertiary carbocation, which we know is more stable than a secondary. So a methyl shift resulted in a more stable carbocation.